Section. Introduction. We're here to discuss the recent progress in large language models, LLMs, which have made significant strides in solving complex problems across various fields, such as mathematical reasoning, knowledge reasoning, root cause analysis, and causal inference. This progress is largely due to a technique that breaks down complex problems into smaller language sequences, which we like to call thoughts. Each thought acts as a stepping stone in the problem-solving process, simplifying the task at hand and helping us reach the final solution. When designing these thought steps for problem solving, whether for humans or LLMs, we need to focus on three key aspects: performance, efficiency, and flexibility. Performance refers to how accurately the problem is solved, including the precision of each intermediate thought. Efficiency is about the number of times the LLM needs to be called upon to solve a problem. The fewer, the better, given the high computational cost of LLM inference. Flexibility, on the other hand, refers to the variety of structures that can be used by LLMs when organizing thoughts for problem solving. These structures can take the form of chains, trees, or even graphs, much like human thought processes. There are several existing thought generation paradigms, such as chain of thought, COT, tree of thought, TOT, and graph of thought, GOT. However, each of these has its limitations and none can achieve all three key aspects simultaneously. For instance, direct input-output, EO, prompting works best for simple problems with single-step processes, but it falls short in terms of performance and flexibility. COT and self-consistency COT-SC, allow for step-by-step problem-solving, which improves performance, but they are limited to linear thought structures, which restricts their flexibility. TOT and GOT, on the other hand, allow for more diverse thought structures, but they require the LLM to evaluate intermediate thought steps, which can be computationally expensive and inefficient. To overcome these limitations, we propose a new solution called Everything of Thoughts, XOT. XOT uses reinforcement learning and Monte Carlo tree search, along with lightweight policy and value networks, to train on specific tasks and then apply this training to new problems. This approach effectively incorporates external domain knowledge into the thoughts given to LLMs, enhancing their problem-solving capabilities and improving performance. Once trained, XOT uses Monte Carlo tree search with cost-effective policy and value networks to efficiently search for thoughts and generate complete cognitive maps for LLMs. This eliminates the need for LLMs to explore and evaluate thoughts themselves, thereby improving efficiency. Moreover, Monte Carlo tree search can explore a variety of thought structures, including graph structures, which enhances flexibility. We've tested XOT across a range of challenging problem-solving tasks, such as the game of 24, 8 puzzle, and Pocket Cube. Our results consistently show that XOT outperforms other thought generation paradigms, providing multiple solutions to problems efficiently with just a few LLM calls. This establishes XOT as an effective thought generation approach, opening up new possibilities for problem solving with LLMs. Section Summary. Recent advancements in large language models, LLMs, have improved problem solving in various domains by decomposing complex problems into smaller language sequences called thoughts. The design of thought steps for problem solving should prioritize performance, accuracy of solutions, efficiency, minimizing computational cost, and flexibility, diverse thought structures. Existing thought generation paradigms have limitations in achieving all three attributes simultaneously. To address these limitations, we propose a novel solution called Everything of Thoughts, XOT, that leverages reinforcement learning and Monte Carlo tree search to pre-train on specific tasks, improving performance, efficiency, and flexibility. Experimental results demonstrate XOT's superior performance and multiple solution capabilities, establishing it as an effective thought generation approach for LLMs. Section. Background. In this paper, we discuss the concept of using language learning models, LLMs, to solve complex problems. This is achieved by breaking down the main problem into smaller, manageable steps. Each step, or thought, can be expressed as a sequence of prompts for the LLM to follow, aiding in problem solving. These thoughts can be organized in various ways, such as linear chains, hierarchical trees, or interconnected graphs, depending on the best approach to reach a solution. We explore several methods of structuring these thoughts. The first is the input-output (IO) method, which is a straightforward way of instructing LLMs to solve a problem without providing any intermediate thought processes. The second is the chain of thought, COT, method, which breaks down problem solving into a sequential chain of thoughts, allowing LLMs to tackle complex problems step by step. The third is the self-consistency COT-SC method, which uses multiple instances of the COT to generate multiple outputs from LLMs. This method selects the best results from multiple LLM outputs, providing more robust and consistent results compared to the standard COT method. We also discussed the tree of thought, TOT, method, which organizes thoughts in a tree-like structure and uses search algorithms to expand the tree in search of an optimal solution. However, this method relies on LLMs themselves to evaluate thoughts, which can be costly and inefficient. The graph of thought, GOT, method extends the TOT approach by generating graph-like thought structures. While this method allows for more flexible thought structures, it still requires multiple LLM inference calls for evaluation, which can be computationally expensive. We introduce a new framework called XOT, Everything of Thoughts. This framework combines LLMs with a Monte Carlo tree search, MCTS, to enhance the thought generation process, helping LLMs solve complex problems. The XOT framework consists of two main components, an MCTS module guided by policy, value networks, and an LLM solver for thought revision and inference. The MCTS and policy, value networks are trained to explore potential thought structures for a specific task through simulated scenarios. The data collected during this process is used to train the policy and value estimation model, which is then used to guide the MCTS in searching for a thought trajectory to aid LLMs in problem solving. The main goal of using the thought generation paradigm for LLMs is to find the best way to break down a complex problem into several smaller steps. Each step aims to change the current state of the problem, eventually leading to the solution of the main problem. This process can be thought of as a Markov decision process, MDP, where the current state represents the current status of the problem, the action represents the solution or action taken to tackle a problem, and the reward reflects the overall evaluation of the solution to the original problem. A one-step thought is a combination of one-step state and action. The generation of complete thoughts can be seen as the effort to find a thought trajectory that maximizes the accumulated reward to solve the overall problem. Section Summary. In order to address complex problems, thoughts can be expressed as linguistic prompt sequences for language model-based models, LLMs, to facilitate problem solving. These thoughts can take the form of linear chains, hierarchical trees, or interconnected graphs. The XOT framework combines LLMs with Monte Carlo tree search, MCTS, to enhance the thought generation process, allowing LLMs to efficiently resolve complex problems by exploring potential thought structures and refining them through collaboration with MCTS. Section. Thoughts searching with MCTS. We're going to discuss a method called thought searching with MCTS, which is a way of aligning thoughts within a language model as a state-action pair. This method is beneficial because it allows us to explore the best path using a combination of Monte Carlo tree search, MCTS, and reinforcement learning, RL. This process is iterative and involves three main stages: selection, expansion and evaluation, and backpropagation. It relies heavily on the use of neural networks, which estimate the value and action probability for a given state. The goal is to speed up the search process by reducing the number of rollouts, similar to the approach used in AlphaGo 0. Let's break down each stage. 1. Selection. The algorithm starts at the root node and chooses an action from the available set for single-step thought generation in the current state. This continues until a leaf node within the current tree is reached. The selection is guided by the PUCT algorithm, which aims to maximize the upper confidence bound. This involves the Q value of a state-action pair, the predicted prior probability of selecting an action given the state, and the count of times an action has been chosen in a state. The selection process continues until an unexplored node is found. 2. Evaluation and expansion. When a previously unselected leaf node is reached, we expand to the state for the next step for new thought exploration. This involves evaluating its value and action probability on the state, which are modeled by neural networks. These two values are kept and stored for backup purposes, and the state is marked as visited. 3. Backpropagation. After expanding a leaf node, the algorithm updates all the Q values. For unexplored nodes, this update involves calculating the average of its estimated value, while for terminated nodes, it's based on the true reward. The visit count for each state action pair is also increased. A simulation is completed after a sequence of selection, evaluation, expansion, and backpropagation steps. After conducting multiple simulations, we proceed to the next step by selecting an action at state using a probability distribution. This distribution is proportional to the visit count raised to the power of a temperature constant that regulates the level of exploration. The simulations allow us to compile a dataset for each sample state containing the state, the search probabilities, and the ground truth value obtained by accumulating rewards along the trajectory starting from the state. We can then train a combined policy and value network to minimize the discrepancy between the predicted value and the actual value, while also maximizing the alignment between the action probabilities produced by the neural network and the search probabilities. This training iterates alongside the simulation process to continually enhance the performance of the network, resulting in progressive improvements in thought-searching capabilities. Once trained, we use the network to guide the MCTS in generating a thought for a new problem, which assists the language model in solving it. MCTS is used to perform simulations aimed at thought-searching and problem-solving. In each simulation, the network is used to guide the MCTS in its search for a thought trajectory. Throughout the training process, the network incorporates external information related to the state and action quality. This information helps language models understand the world model, enhancing their long-term reasoning and planning abilities. After the simulation, we record the visit count and the thought trajectory is obtained based on the number of solutions required. For single solutions, the action with the highest visit count is selected. For multiple solutions, we sample thought trajectories following the probability distribution and remove duplicates. This results in one or multiple thought trajectories that consist of a sequence of state action pairs for problem solving. These trajectories are then transformed into text sequences that are concatenated to form a prompt sequence provided to language models. It's important to note that MCTS may not always provide the globally optimal thought trajectory to directly solve the problem flawlessly. Therefore, the thoughts extracted from MCTS serve as a reference thinking process for the problem, aiding language models in a supportive capacity. The language models will use their internal knowledge to review the extracted thought, identify errors in the thought trajectory, and then ground its knowledge in collaboration with the MCTS to revise and refine the thought. The revision process is iterative in nature. If the language model identifies an error, it results in an error state within the thought. If no error is found, the thought remains unchanged. Starting from the parent state of the error state, MCTS conducts an additional set of simulations, ultimately yielding a revised thought for the language model. In scenarios involving multiple solutions, each solution undergoes this process individually. Upon the completion of the revision, we supply the language models with the revised thoughts for problem solving. The revision process can be repeated several times to enhance the reliability of the answer. This collaborative MCTS language model framework nurtures a mutually beneficial process for both components, ultimately contributing to the overall performance of problem solving. Since language models are solely utilized for identifying errors during the revision process with only one call, the efficiency of the method is effectively maintained. The collaborative revision framework harnesses the strengths of both MCTS and language models. MCTS efficiently and flexibly generates candidate thoughts for language models through simulations, while language models use their internal knowledge to revise and ground these thoughts within the MCTS framework, effectively turning MCTS into a world model for language models. This process ensures the generation of high-quality thoughts for problem solving. Section Summary. The section describes a method called thought searching with MCTS, which combines Monte Carlo tree search, MCTS, and reinforcement learning, RL, to explore optimal thought trajectories. The process involves selection, evaluation and expansion, and backpropagation phases, guided by neural networks. The trained networks are then used to guide MCTS in generating thoughts for problem solving, which are revised iteratively by a language model, LLM, to enhance their quality. This collaborative framework improves problem-solving performance by leveraging the strengths of both MCTS and LLMs. Section. Experiment. We've carried out a comprehensive evaluation of our XOT method, comparing it to several other techniques across 3 complex tasks: the game of 24, the 8 puzzle, on a 3x3 grid, and the 2x2 pocket cube. These tasks are intricate, often requiring multiple steps to complete and potentially having more than one solution. To gauge the effectiveness of our XOT method, we compared it to other methods such as IO, COT, COT-SC, TOT, and GOT. We used both GPT 3.5 and GPT-4 for these evaluations. It's important to note that we set the temperature and top_P to 0.0 for all language model invocations. Our model's policy and value networks use a shared multi-layer perceptron, MLP, architecture with 2 layers and hidden units arranged in a 128/256 configuration. 2 heads connected to the MLP predict the value and policy separately. This design results in a significantly smaller model compared to language models, making it much more efficient. We trained this model through 3 iterations, with each iteration consisting of 10 self-play episodes for Monte Carlo Tree Search, MCTS. For each task, we evaluated the accuracy of each method on the test set. We also tracked the number of language model invocations required for all methods to solve a problem, as well as the number of times the function was invoked in the case of XOT. This function is a much smaller model compared to language models. In situations where there are multiple solutions, accuracy is calculated as the percentage of problems for which any of the answers provided by each method is correct. We also calculated the average percentage of correctness across all solutions offered, which we call multi-solution accuracy, multi-ACC. Additionally, we recorded the total count of distinct solutions provided by each method, regardless of their correctness, represented as #sol. We set the maximum solution number to 3 for all problems in multi-solution scenarios. The game of 24 is an arithmetic challenge where the goal is to use 4 numbers between 1 and 13, along with basic arithmetic operations, addition, subtraction, multiplication, division, to achieve a final result of 24. This game can have multiple valid solutions. We collected a dataset of 1,362 games ranked by human solving time, covering a range of difficulty levels. For our testing phase, we randomly selected 137 games, ensuring coverage of various difficulty levels. The remaining 1,225 problems were used to train the policy value networks with MCTS. In this task, the thoughts refer to the 3 intermediate equations, while the state includes the available numbers, from 1 to 4, for creating the equations. Actions involve selecting 2 numbers and an operator to form an equation, and the reward is set to 1 if the final equation is both valid and results in the number 24, using each of the input numbers exactly once. Otherwise, it is set to -1. Performance is measured by calculating the success rate across the 137 test games. For the IO method, we used 5 in-context examples. For COT, we added 3 intermediate equations to each input-output pair. For TOT, we asked the language model to categorize each thought candidate for intermediate selection at each step. For comparison, we conducted experiments on both the top 1 candidate and the top 3 candidates being retained, where the number of branches retained for exploration at each step is represented by B. For GOT, we used the language model to generate one-step thought candidates in the same way as TOT. Then we directed the language model to select the top 1 thought from all candidates for merging the thoughts. We also examined a COT-SC baseline, which derives the majority output from 10 COT samples. For XOT, we performed 200 simulations for each action taken, and this count is increased to 500 during the thought revision process. In the multi-solution scenario, the IO, COT, and COT-SC methods each include 5 examples, with each problem having 1 to 3 different solutions. For TOT, the top 3 candidates at the final step are considered as different solutions. Rather than keeping only the top 1 thought, GOT is instructed to select between 1 to 3 thoughts from all candidates at each step to generate a wider range of solutions. As for XOT, after performing simulations on MCTS, we sample 500 thought trajectories for exploration and remove duplicates. The top 3 thoughts with the highest counts are preserved. Section Summary. The authors conducted an extensive evaluation of their XOT approach by comparing it to several baseline methods across 3 challenging tasks: the game of 24, the 8 puzzle, and the 2x2 pocket cube. They used GPT 3.5 and GPT-4 for the evaluations and assessed the accuracy of each approach on the test set. They also tracked the number of model invocations required and the number of distinct solutions provided by each approach. Section. Results. The results section of the paper presents a comparison of the performance of various methods on a given task. The standout performer is XOT, which consistently outperforms other methods on both GPT 3.5 and GPT 4 models. Without any revisions, XOT achieves an accuracy of 61.31% and 63.50% on GPT 3.5 and GPT 4 respectively. However, when revisions are made, the accuracy of XOT improves significantly to 79.56% and 74.45% on GPT 3.5 and GPT 4 respectively. This highlights the effectiveness of XOT and shows that the revision process greatly enhances performance, with only a slight increase in the use of LLM and the function denoted as f_theta. Interestingly, the revision process in XOT reduces the performance gap caused by the modeling ability in this task. For instance, XOT with GPT 3.5 achieves higher accuracy after revision compared to GPT 4. On the other hand, the best performing baseline, TOT, B=3, on GPT 4, achieves an accuracy of 60.58%. However, it requires a significant number of LLM invocations, 39.83, which results in inefficiency. In contrast, XOT is much more efficient, requiring only a single LLM inference without revision and less than 1.4 calls with revision. Even though XOT requires some inference calls for the function f_theta, the model is significantly less complex than LLM, making it a much more efficient approach. The performance of GPT 3.5 and GPT 4 models across different methods in the multi-solution scenario is also presented. Overall, XOT remains the best performing approach in terms of accuracy and multi-ACC, significantly outperforming other methods. Its GPT-4 version can even achieve over 90% accuracy. Although XOT does not generate the most number of answers compared to other methods, it generates more accurate answers, as its multi-ACC significantly outperforms other approaches. Notably, generating multiple solutions does not significantly increase XOT's complexity, as it only requires 2.31 LLM calls with GPT-4 and around 100 calls for a smaller function f_theta, making it remain efficient. Overall, the remarkable performance of XOT in the multi-solution scenario demonstrates its ability to generate complex thoughts, making it a flexible approach. The 8 puzzle is a classic sliding puzzle game that consists of a 3x3 grid with 8 numbered tiles and 1 empty space denoted as. The goal is to rearrange the tiles from a given initial configuration into a target configuration. The maximum number of steps necessary for the optimal solution of the 8 puzzle is 31. This problem is categorized as an NP-complete problem and may have multiple solutions. For the task setup, we randomly generated 419 solvable 8 puzzle problems, with 300 instances allocated for training and 119 instances for testing. All generated problems can be solved within 9 steps. The action space includes 4 directions: up, down, left, right. Note that the legal action space for each problem state may vary due to the dynamic position of the empty space. As shown in the table, the thoughts refer to the step-by-step move, and the puzzle state after the move. The EO prompt is extended with 3 in-context examples. In the COD approach, each input-output pair is enriched by incorporating intermediate legal action sets, the current action, and the current state. In TOT, at each stage, a set of one-step thought candidates are derived from the LLM, from the current set of legal actions. We impose a maximum step limit of 9 since all generated problems can be solved within this range. The 8 puzzles rules are conveyed through a system message, including detailed explanations of each action's execution. Similarly, we perform 20 simulations for each action taken with XOT, and increase this number to 50 for thought revision processes. In the multi-solution scenario, all of the IO, COT, and COT-SC prompts consist of 4 examples. Each problem is presented with 1 to 3 distinct solutions. For TOT, B=3, and GOT, K=3, the maximum number of steps is increased to 12, as correct solutions may not always be optimal and could exceed 9 steps. In the case of XOT, after conducting simulations with MCTS, we sample 50 thought trajectories for exploration and select the top 3 thoughts with the highest counts. The inherent spatial complexity of the 8 puzzle, the need for long-term planning, and the presence of invalid actions create a significant challenge for LLMs, which rely solely on textual data as input. This challenge is starkly evident in the poor performance of the baselines on both GPT 3.5, where its I/O prompting achieve a mere 0% success rate. XOT successfully addresses this issue by supplying thoughts acquired from MCTS, thereby infusing external knowledge into the problem-solving process. This augmentation empowers LLMs to tackle problems that were previously insurmountable. In summary, when using GPT-4, XOT achieves an accuracy of 50.42% without revision and 93.2% with revision in the 8-puzzle task, outperforming the best baseline, TOT, B=3, which only achieves 13.45% accuracy. Additionally, XOT demonstrates efficiency, requiring approximately 1.5 LLM calls and around 55 calls to the function f_theta, while delivering significantly superior performance. The multi-solution performance presented in the table confirms that the XOT method continues to outperform other methods for both GPT 3.5 and GPT 4 models in terms of accuracy and multi-ACC, whether or not revision is applied. It's worth noting that the revision process is particularly beneficial for GPT 4, as it improves the multi-ACC from 29.13% to 76.33%. These results once again demonstrate that XOT can effectively generate complex thought structures for complete multi-solutions with high performance and efficiency, making it particularly suitable for this task. Section Summary. The XOT method consistently outperforms other baselines on the 8-puzzle task, achieving high accuracy without revision and even higher accuracy after the revision process. XOT's performance is significantly better than other approaches in terms of accuracy and efficiency, making it a flexible and efficient solution for generating complex thoughts in the multi-solution scenario. Section. Pocket Cube. We're going to talk about a simplified version of the Rubik's Cube puzzle, known as the Pocket Cube. This 2x2 cube puzzle aims to have all its faces restored to a single color by performing various rotations. The maximum number of steps to solve this puzzle optimally is 11, and it's a complex problem that can have multiple solutions. This makes it a tough challenge for large language models, LLMs. To set up our task, we start with a pocket cube where all faces are the same color. We then randomly perform 5 actions from the 27 possible Rubik's Cube moves. This gives us 1,000 training samples and 183 testing samples. All the problems we generate can be solved in 4 steps or less. To make things simpler, we reduce the 27 possible moves to just 9. U, U2, R, R2, F, F2. We use these in our experiments with both the baseline models and our new method, XOT. Our XOT setup involves augmenting the input-output (EO) prompt with a single example. In the context-to-thought (COT) method, we enrich each input-output pair by including intermediate actions and states. In the thought-to-thought (TOT) method, we get one-step thought candidates from the LLM at each stage and ask the LLM to classify each candidate for intermediate selection. We set a maximum step limit of 4, as all our problems can be solved within this limit. We also provide a system message that explains the rules of the Pocket Cube, including the action space and how each action is executed. For XOT, we run 20 simulations for each action taken and increase this to 500 for revision. The Pocket Cube task is a challenge that requires spatial imagination skills, which makes it difficult for LLMs. As expected, most of the baseline models perform poorly on this task, with some achieving 0% accuracy. The best performing baseline, TOT, B=3, with GPT-4, only manages a success rate of 19.57%. In contrast, XOT can achieve over 45% accuracy without revision and over 75% accuracy with revision, making it an expert in solving this task. This success is due to the use of external knowledge from Monte Carlo tree search, MCTS, which helps LLMs solve problems they would otherwise struggle with. Notably, XOT is highly efficient in this task, requiring only 1.55 and 1.54 LLM inference calls for GPT 3.5 and GPT 4, respectively. In a multi-solution scenario, XOT continues to perform remarkably well, achieving over 91% accuracy and over 77% multi-ACC with GPT 4. The revision process plays a significant role in improving the performance of XOT with both GPT models. The closest competitor in this setting is GOT, K=3, with GPT-4, which achieves an accuracy of 30.50% and a multi-ACC of 16.85%, but it requires a significantly higher number of LLM invocations compared to XOT, 13.36 versus 4.08. We also conducted an ablation study to understand the impact of the number of revisions on the performance and efficiency of XOT and the sensitivity of performance to the completeness of the provided thoughts. This helps us understand how to improve XOT's performance and the importance of providing complete thoughts in complex problem-solving tasks. We found that the performance of each task can be further improved through multiple revisions of the thought using the MCTS LLM collaborative framework. As the number of revisions increases, both GPT 3.5 and GPT 4 models show improved performance. However, this comes at the cost of increased inference times and model calls, primarily due to the need for more interactions to generate revised thoughts. For the Pocket Cube task, the accuracy of both models improves with an increase in the number of revisions. GPT 3.5 starts at an accuracy of 45.36% without revision and improves to 84.70% after 3 revisions. GPT 4 begins with an accuracy of 45.9% and reaches 83.61% after 3 revisions. The number of LLM invocations does not increase dramatically with additional revisions, even though the guiding function is called more times to guide simulations. Considering the significant difference in inference costs between LLM and the guiding function, increasing the number of revisions to achieve better performance appears to be a favorable trade-off. Section Summary. The 2x2 Pocket Cube is a simplified version of the Rubik's Cube puzzle, and its optimal solution requires a maximum of 11 steps. This problem is challenging for language model learners, LLMs, and is considered nitrogen monophosphide complete. However, the XOT method, which incorporates external knowledge from Monte Carlo tree search, MCTS, achieves high accuracy, over 75%, in solving this task, outperforming other baselines. Additionally, the number of revisions in the XOT method can further improve performance, and providing complete thoughts is crucial for complex problem-solving tasks. Section. Incomplete thought. In this section, we're examining how language learning models, LLMs, perform when they're given incomplete information, specifically when the final step of a thought process is missing. This is similar to situations where Monte Carlo tree search, MCTS, might provide incomplete or inaccurate thoughts. We're testing whether LLMs can solve problems on their own, without relying solely on the thoughts provided by MCTS. We compared the performance of different models across 3 tasks and found that incomplete thoughts significantly reduced performance in all tasks. GPT 3.5 was more effective than GPT 4, with GPT 3.5 failing to achieve any accuracy on several baselines. However, when using GPT 4 with our approach, XOT, we saw satisfactory performance on the game of 24 and 8 puzzle tasks, with accuracy over 40%. But, for the more complex Pocket Cube task, accuracy dropped to just 6%. This shows that for complex tasks, LLMs are very sensitive to the completeness of the thoughts provided. If steps are missing, performance can drop significantly. We also looked at examples of thought structures generated by XOT for all 3 tasks when multiple solutions were required. We found that the generated thoughts intertwined during intermediate steps and converged towards the final goal. This resulted in a thought structure that resembled a graph, demonstrating the flexibility of XOT. In the game of 24, there were multiple ways to reach the goal of 24 from the initial state, and XOT was able to predict these trajectories. In the 8 puzzle example, we saw instances of reflection in the thought structure, showing XOT's capacity for self-reflection. In the Pocket Cube task, XOT identified 4 distinct pathways to reach the goal state, leading to successful problem-solving across multiple solutions. In summary, our approach, XOT, significantly improves the performance of LLMs by introducing a streamlined thought trajectory revision process. This is a fundamental shift from traditional problem-solving approaches and results in substantial performance enhancements across a range of tasks. XOT excels in solving the game of 24 and demonstrates its ability to overcome challenges requiring spatial reasoning, such as the 8 puzzle and Pocket Cube, which were previously challenging for LLMs. The use of LLMs for decision-making and planning is a growing area of research. The process involves breaking down complex problems into subtasks, similar to how humans solve problems. Various frameworks have been designed to facilitate problem decomposition, leading to enhanced solutions derived from LLMs. Our approach, XOT, stands out from these by achieving superior performance, efficiency, and flexibility, embodying the concept of comprehensive thought generation. Enhancing the capabilities of LLMs through the incorporation of external models is an effective strategy for improving their overall quality. For example, ChatGPT uses reinforcement learning from human feedback to enable LLMs to adhere to human guidance, resulting in a substantial enhancement of their truthfulness and a reduction in toxic output. Similarly, GLAM uses online reinforcement learning to align LLMs' knowledge with the broader environment, enhancing their ability to generalize to new objects or tasks and ultimately improving their performance. These studies underscore the considerable potential in augmenting LLMs with reinforcement learning techniques. Section Summary. In this section, the authors conduct an ablation study to test the performance of language models, LLMs, when provided with incomplete thoughts. They find that incomplete thoughts lead to a significant drop in performance across different tasks, highlighting the importance of providing complete thoughts for complex tasks. Additionally, the authors present examples of thought structures generated by their approach, XOT, which demonstrate its ability to grasp complex thought structures and foster diverse and creative thinking in LLMs. Overall, XOT significantly improves the performance of LLMs and excels in solving tasks that require spatial reasoning. Section. Discussion. Let's talk about how we can generalize the use of XOT. Right now, we're using XOT mainly for problem solving and search tasks. But we believe it can be used for a wider range of problems, especially those that can be broken down into smaller tasks with clear goals. The Monte Carlo tree search, MCTS, method we're using in XOT is perfect for these kinds of tasks and can be adapted to handle more complex problems. We should also mention that MCTS isn't the only method that can be used in XOT. We can replace it with other supervised or reinforcement learning models to explore and generate thoughts. These models can act as a co-pilot, providing real-world knowledge to large language models, LLMs. This opens up exciting possibilities for future research, allowing LLMs to plan and solve problems more effectively. However, there are some limitations to using XOT. For one, we need to train additional policy and value models to speed up the inference process. This training requires data from real-world environments, which can add extra costs and effort. But it's important to note that these policy and value models are much smaller and more efficient than the LLMs they're supporting. So, the extra costs are relatively low, especially for the tasks we're focusing on in this study, which have clear steps and goals. In the future, we plan to find ways to make the training process for XOT more efficient, especially for tasks with less clear objectives, like multi-agent planning and code generation tasks. This will help us apply the XOT framework to a wider range of applications. In conclusion, the XOT framework we've presented in this paper represents a major step forward in thought generation for LLMs. It challenges the limitations of the Penrose triangle by achieving performance, efficiency, and flexibility all at once, something that existing prompting methods can't do. We've accomplished this by combining MCTS with low-cost policy and value networks, providing real-world knowledge to LLMs, offloading the search for thoughts, and allowing for unrestricted exploration of thoughts. Our framework, which involves both MCTS and LLMs, improves the quality of thought generation. We've tested it on 3 complex real-world problems: the game of 24, the 8 puzzle, and the pocket cube. The results show that our XOT framework performs significantly better than existing prompting methods, especially when dealing with problems that have multiple solutions.